Alright, so sorry we couldn't meet Friday, and then we missed that snow day before then too, so we need to do something to catch up. So here it is. So I'm going to talk about the remainder of Chapter 1 in Gamelin and Green. I talked about this a little bit in class already, but I think I'll do it again. Section 6 is on continuous functions. So here's the definition. If we have two metric spaces, x with metric d, y with metric rho, a function from x to y is continuous at a point if we take a sequence converging to that point, and that implies that the values of the sequence converge to the value of the image of the point. And then a function is continuous if it's continuous at each point in its domain. So this is sometimes called the sequential definition of continuity. Now, perhaps you're more familiar from calculus with the Epsilon-Delta definition of continuity, right? So this, after the if and only if, is the Epsilon-Delta definition, right? For each epsilon greater than 0, there exists a delta greater than 0 such that whenever z is within distance delta of x, that implies that the image f of x is within epsilon units of f of z. So this is the so-called Epsilon-Delta definition of continuity in a metric space. And Theorem 6.1 shows that they're in fact equivalent. Now the proof is very contrary. It's essentially both the forward and the backwards are, let's see here, some sort of contradiction. Let's see here. So suppose there exists an epsilon greater than 0 such that for each delta there is a z within delta units of x, and yet the distance from f of x and f of z is larger than or equal to epsilon, right? In other words, we're violating the criteria of the Epsilon-Delta characterization of continuity at the point. And so if that's the case, if we consider delta equal to 1 over k, then we can select z sub k, which is within distance 1 over k from x, and the image of those will be more than epsilon units away from f of x, like that. Then clearly z sub k converges to x, because of course as k goes to infinity that goes to 0, which means the distance between x and that is 0, which is to say that zk goes to x. And yet, because of this criteria over here, f of zk does not go to f of x, because it's never getting close, right? It's always larger than epsilon, at least for this choice, this particular sequence. And remember, the sequential definition requires all convergent sequences to produce convergent images for the continuous function at the point. So this is not that, which implies that f is not continuous. So what we did was we showed that not meeting the Epsilon-Delta criteria implies not having continuity. All right, and then turn that around. That gets us that the Epsilon-Delta characterization of continuity implies the sequential characterization of continuity. All right, and then conversely, suppose that we don't have sequential continuity at x, and in other words, there's this some sequence going to x, and yet the values of the sequence don't go to f of x. And he says, Gamelin and Green suggest we can find a subsequence. This is my notation, not theirs. X sub nj, such that the subsequence is further than epsilon away from the image for some epsilon positive. And so there does not exist a delta greater than 0, such that being within delta units of x implies that we're within epsilon units of f of x. All right. Because of this data right there. Anyway, this proof is very contrary, I would point out. I feel like one direction in this proof I can do directly, and I don't need the kind of backwards thinking that's going on here, but at least one of the directions of this Theorem 6.1 almost always, it seems like, requires some sort of proof by contradiction. Anyway, I digress. Here we go. Theorem 6.2. These are different characterizations of continuity. Alright, so the following are equivalent for a function from a metric space x to a metric space y. F is continuous, the Epsilon-Delta definition of continuity, and this one's new. The inverse image of an open subset. So this is, you could write this sentence a slightly different way. You could say, let V be an open subset of Y, then F inverse of V is an open subset of X. All right, and to be clear, that's for all possible open subsets of Y. In other words, 6.3 says that the inverse image of open sets is once more open. That is a characterization of continuity of a function on a metric space. All right. So let's see here. I think Theorem 6.1 already proves the equivalence of 6.1 and 6.2. So what we're going to do is suppose 6.2 is true and try to get 6.3. All right. So if 6.2 is true, if V is an open, and let V be open in Y, and let X be in the inverse image of this open set, right? By the way, that means that f of x is in V, and since V is open, that implies that there exists, excuse me, yowzers. There exists an open ball of some radius around f of x in V, right? By the fact that every point in V is interior. So, in other words, there exists an epsilon greater than 0 such that this ball of radius epsilon around f of x is a subset of V. But what does that say? Well, that says that we're also assuming 6.2, right? 6.2 says that if there exists a delta such that implies this, right? If you're within delta units of of x, then you're going to be within epsilon units of f of x. The image will be anyway. In other words, if z is in the ball of radius delta centered at x, that implies that f of z is in the ball of radius epsilon centered at f of x. All right. So, so the f of the, so what this says then is that the image of the ball of radius delta centered at x, which is this, is a subset of the ball of radius epsilon centered at f of x, which of course is a subset of V. Alright, so what does that say? Well, that says that this ball of, it says that this ball of radius delta centered at x is in the inverse image of V, because f of that is a subset of V. That means that f inverse of V contains that ball. And so each point in the inverse image of V is contained in an open ball, which is to say it's interior, and it follows that the inverse image of V under F is open. So that is to say that 6.2 implies 6.3. And then if we can show 6.3 implies 6.2, or if we could show 6.3 implies 6.1, we'd be done. I think that the proof here is to show that 6.3 implies 6.2. Suppose 6.3 is true, which is to say that the inverse image of open sets is open. We're going to try to work on 6.2, which is the Epsilon-Delta characterization of continuity. So let x be an x, and let epsilon be positive. And, okay, then the inverse image of the ball of radius epsilon centered at f of x is an open set containing x. Alright. Why is that open? Because we're assuming 6.3 is 2. So this is an open set, the inverse image of it's open. Alright. If it's open, that means that there exists a delta centered, so by the way, x is in here. Alright, because x maps to f of x, and f of x is in this ball. Therefore, x is in the inverse image of this thing. All right. So since x is in the inverse image, and this is an open set, that means there exists a delta ball around x, namely b of x delta, which of course is inside this open set. Which is to say, taking f of both sides, that the image of the ball of radius delta centered at x is a subset of the ball of radius epsilon centered at, goodness gracious, I'll fix it. There we go. Centered at f of x, which is to say that we have shown that 6.3 implies 6.2. All right. Okay. Anyway. So there you go. 3 different characterizations of continuity of a function. The sequential definition, the epsilon-delta definition, and then 6.3, which I would refer to as the topological definition of continuity, that the inverse image of open sets is once more open. 6.3 will become the definition of continuous function when we reach the next chapter. Let me go on. All right. What's uniformly continuous mean? So uniform continuity means that for each epsilon greater than 0, there exists a delta greater than 0, such that whenever we're within delta units of x and z are within delta units, then the image f of x and f of z is within epsilon units. So the uniform is to say that the delta doesn't depend on the chosen point. Like there is pointwise continuity would fix x, and then delta might have an implicit sort of x dependence. Here there's no x dependence. It's just there's one delta for any choice of x. And all right. Anyway, theorem 6.3. Let x and y be metric spaces, x compact. Every continuous function from a compact with compact domain is uniformly continuous. All right. So there's a proof given in Gamelin and Green, but I'm gonna probably try to. Well, I mean, I'm fine. I'll talk about it for a minute. So if we have x and y metric spaces and x compact, suppose f is not uniformly continuous. That would mean that there exists a delta greater than 0 and points xk and zk such that the distance between xk and zk was less than 1 over k, whereas the distance between the images f of xk and f of zk was greater than or equal to epsilon, right? Let's see here. And then they say pass to a subsequence, and I'll use n sub j for the subsequence. Then as the distance between these, of course, goes to 0 as k goes to infinity, we should likewise find that a subsequence also goes to x, where x is, of course, where x sub k is going to as k goes to infinity. I think to say otherwise would be to violate this assumption. Anyway, so we have f of x in the subsequence, x of n sub j, goes to f of x, and also f of z of n sub j goes to f of x. Consequently, we have f of x of n sub j comma f of z sub n sub j less than or equal to, by a triangle inequality, this. But both of these are going to 0, right? Which says that this is going to 0, but that violates the fact that the star right here, because we'd assume that, in fact, these don't converge. I mean, they can't be made arbitrarily small as k goes to infinity, and yet they can be. Well, anyway, I'm not entirely convinced by my proof, and I really want to get on to the next chapter. You'll forgive me if I go on here. Again, this really should be something that you get into more depth in a later course. I'm just trying to give you a sense of how things are done in metric spaces. My apologies if I missed some details here and there. Now, next up is section 7, which is on normed linear spaces. All right. So let's talk about this for a little bit. First of all, a norm is something that we give on a vector space. All right. we'll use this symbol for vector space in this section. A norm is a function that maps x to a number, a real number, such that x is non-negative. It's 0 only if it's the 0 vector. We have homogeneity. We can pull out the absolute value of a scalar. That scalar could be complex. All right, so that would be modulus, if you like, or the square root of the real squared plus the imaginary squared square rooted. If it's a complex number, right? Like if it's 2 plus 3i, that would be the square root of 13. Anyway, then of course we have triangle inequality for the norm. All right. So a norm is a vector space with some notion of vector length, and we call that vector length function the norm. There are many examples of normed linear spaces, which I will refer to as NLSs going forward. So here's some of the examples that Game 1 gives us. Rn with the Euclidean norm, or the 2 norm. Rn with the 1 norm. In other words, it's the sum of the absolute value, that's the coordinates. Rn with the p norm. It's the pth root of the sum of the pth powers of the absolute value of the ith coordinate summed I equals 1 to n. There's also a max or a sup norm, where you take the maximum of the absolute value of all the coordinates like so. That's sometimes called x sub infinity. In the sense that this kind of is what you get taking p going to infinity. It, in some sense, becomes that. There is more. You can look at sequences with respect to the p norm. You can look at a set of bounded p norm bounded sequences. In other words, only look at those sequences for which this quantity is less than infinity. That gives you a normed linear space. You can talk about the sup norm on sequences, which you take the supremum of all, the absolute value of the sequence. That will define a norm. More interesting, perhaps, if you have a non-empty set, you can look at the bounded real valued functions on that set. You define the norm to be the supremum of the absolute value of the functions, absolute value of the function's values with inputs taken from S. That gives you the so-called subnorm on Vs. You could also add the assumption of continuity. That would give you BCS, the bounded continuous functions on S. For example, if you look at the bounded functions with the domain being natural numbers, that gives us L infinity, which we talked about up there as well. Right? Because a sequence is a function with the domain being the natural numbers. And then, as he says, any subspace of the bounded functions on S also inherits a norm like bounded continuous, where X is a metric space. I guess I should have mentioned, when I said a BCS up here, that was wrong. I also need to know that S is a metric space. Otherwise, how do you define continuity, right? Fair enough. Now, last but not least, we could talk about the continuous functions with domain 0, 1, right? This has many norms. Here are some of the ones we could choose. We could give it the 1 norm, integrate the absolute value from 0 to 1. We could give it the 2 norm, take the square root of integrating the absolute value squared from 0 to 1. You can give it the p norm, integrate the pth power of the absolute value from 0 to 1, and then pass to the 1 over p root. These are kind of obviously continuous extensions of the norms that we mentioned on LP above. So anyway, when you study functional analysis, you'll have plenty of time to investigate all of these and all of their nefarious various properties. I'm just mentioning them in passing here. I just want you to know what a normed linear space is and just some of the basic results. That's all we're after here. So one of the first things we're after is to know that if you have a normed linear space, then it's also a metric space where you induce the norm, induce the metric by just the length of the displacement vector between the points. So you take x, you take y, you take the difference. I think of that as being the vector which points from y to x. And the length of that vector, well, that's going to be the distance in what's called the norm topology. Anyway, that's the metric induced from the norm. All right. And so to prove it's actually a metric, that makes a kind of reasonable question for you guys. So we're assuming that that's a norm. So we know that it's non-negative, so that it says that the distance from x to y is non-negative. Good. That's one of the things we need for a metric. We also need that the, what was that, indiscernibility, or was it? Anyway, the distance from x to x should be 0, right? Well, the distance from x to x is the norm of x minus x. In other words, distance from x is the norm of 0, which by definition was 0. So that's another thing we need for D to be a metric, right? We also need symmetry. So here's symmetry. Distance from x to y is the norm of x minus y, which by vector space technology, if you will, factor out the -1, and then use property of the homogeneity of the norm to pull out the absolute value of -1. And there you go. That's the distance from y to x is equal to the distance from x to y. That's comforting. Not surprising, but comforting, I suppose. And then finally, the triangle inequality is going to follow from the triangle inequality. So if you look at the distance from x to z, that would be the norm of x minus z, which we could add and subtract y judiciously, and in so doing, apply the triangle inequality, bop, bop, and that, of course, is the distance from x to y plus the distance from x to z. So there you go. D, the induced metric satisfies. It's non-negative. It's only 0 when you're, feeding it the same input. It's symmetric, and it satisfies the triangle inequality. In short, D defines a norm on the normed linear space. It is the so-called induced norm. And by the way, the topology, the metric topology, although it seems like that terminology is really belonging in the next chapter. Okay, well, you'll forgive me. The metric topology given by the induced metric from the norm is the so-called known as the norm topology of the normed linear space. For example, an open ball in the presence of a norm is y in the vector space such that the norm of y minus x is less than epsilon. That's the ball centered at x, all right? And if we said a sequence was to converge in a normed linear space, that would mean that the limit as j goes to infinity of the norm of xj minus the proposed limit is equal to 0. All right? So, a little bit more to say, which is that addition and scalar multiplication and also the assignment of norm are themselves continuous functions on a normed linear space. All right. Or, I guess to be picky, they're really continuous functions from the Cartesian product of the normed linear space in itself for addition, or they're continuous functions from the field of scalars across the normed linear space to the normed linear space, right? Or in this case, it's a continuous function from the normed linear space to the real numbers. So the domain and the codomain of these various different maps is rather varied. So to really be picky about the continuity, we would need to take that into account. And I try to do that in what follows here. But there's probably, to be really, really picky, there's probably a few more sentences which should be given. But this is the heart of the matter, which is that if we take, this difference, we can rewrite it as the sum of these differences, which by the triangle inequality gives me that. So if I know that xn is going to x, and if I know that yn is going to y, then it says that this plus that minus this plus that is going to 0, which is to say that, that addition is continuous. And similarly, if I have xn going to x, and if I look at this, that shows me that cx is going to, or rather cxn is going to cx as n goes to infinity. So that gives me half of the so I think this estimate gives me both kinds of continuity I want on both copies of the normed linear space that defines the addition map. This inequality gives me the continuity with respect to the x input that I'm interested in. All right. So on the other hand, I might look at a real sequence, and if I look at that real sequence, I can factor the x out like this, and then this, if the real sequence, if cn is going to c as n goes to infinity, well then this goes to 0, which shows you that that goes to 0, which is to say that as we feed a sequence into the scalar component, the scalar entry of scalar multiplication, we get continuity. So we get continuity in both inputs for both scalar multiplication and vector addition, which is to say that vector addition and scalar multiplication are continuous. So, I think it's a good book, but I do think there's some, if you don't feel like his arguments are convincing as they pertain to metric spaces, well, you're probably not wrong. There's probably something missing here. It's a bit rushed, this chapter, but I do think it serves its purpose. I wouldn't try to replace this chapter in Gamelin and Green. It's not a replacement for an analysis, a text. It's just trying to set the stage for topology, really. So, all right, and then finally, this inequality here is what's needed to show that the assignment of x goes to the norm of x is itself a continuous function. All right. So next up, he talks about linear transformations, right? Or you could talk about linear functionals. So that would mean that the output's not just a vector space; it's in fact the field in question. And so this is one of the more important definitions that one has to really try to internalize and come to terms with as you study this material. This is how we define the norm of an operator. So-called operator norm is what's being defined here. So I have a linear operator going from a normed linear space X to I think a normed linear space J. It's said to be a bounded linear operator if it's linear, and the supremum of the norms of images taken from the closed unit ball in X. Right? If this exists, all right, then that's equal to the norm of T. I suppose, depending on the setup, the norm could be, this could be infinite, I suppose. It depends on what we've agreed to allow for our supremum. Some book allows supremums to be infinity as well. But certainly for this to be bounded, this would be finite, all right? And that's so basically you feed all inputs of size less than or equal to 1 with respect to the norm into the operator, and then you look at the length of those, and the largest of that defines the length of the operator. Notice that since we have homogeneity of the operator and we can pull Cx out like that, if you take x to be on the unit ball, well, Cx is still in the vector space, right? And unless this is 0, this can be made as large as you like. So if we don't just focus our attention on the closed unit ball, certainly the values for a linear transformation, which is non-zero, will be unbounded. Duh. I'm sorry. Anyway. This is also nice. If T is a bounded linear operator from the normed linear space x slash to J, then the norm of, and this is T of x, I'm just writing it Tx, pure pressure, Gamelin's doing it, so it must be right. Actually, it's not uncommon to omit the parentheses in this kind of discussion, because after about the 13th time you write T of x, you go like, I don't need to write these parentheses. Anyway, so the norm of the image is less than or equal to the norm of the operator times the norm of the input, and that is lemma 7.3. And its proof is not too bad. You suppose you've got x non-zero point in your normed linear space. You normalize that thing. All right, that gives you a unit vector, which is in the closed unit ball, of course. So since this is the supremum of the image, supremum of the norms of the images taken from the closed unit ball, it immediately follows that the length of the image of the unit vector must be less than or equal to that norm. But then by homogeneity, I can pull out the norm of x from here, and then I can pull it out from there at no extra cost because the norm is already positive, so the absolute values are redundant. And bam, you get that the norm of T of x, and you can omit the parentheses if you like, is less than or equal to the norm of x times the norm of T. All right. And of course, if x is 0, this is trivially true because, well, the linear transformation acting on 0 is 0, And the norm of 0, 0. So 0 equals 0, yay! All right. Lemma 7.4. The set of all bounded linear operators from a normed linear space X to a normed linear space J forms a normed linear space with norm given by the operator norm. So the proof is on page 33, and it's pretty straightforward. I'll let you look at it there. Just wanted to make you aware of this, is that, you know, just kind of like we see in linear algebra, right? We look at linear transformations from a vector space to a vector space, and then all of a sudden we get to go, oh, and guess what? They're also a vector space. This is kind of a similar thing. The space of mappings, appropriate mappings, bounded linear operators from a normed linear space to a normed linear space, is itself a normed linear space. It's kind of neat. Now, so this is the perhaps surprising, I mean, I don't know, personally when I was in graduate school and I saw these things for the first time, I think, in my functional analysis class, they were kind of like, what? But, you know, here they are. Anyway, let me not lather on. So we have X and J normed linear spaces, T a linear transformation, or linear operator. That's just another term for the same thing. Going from, you know, from X slash to J, the following are equivalent. T is continuous. T is continuous at 0, and T is bounded. Ooh. See, that's this bounded. I mean, this and that, I'm kind of like, okay, well, that, I mean, it's, you know, it's linear. So, I mean, the idea that continuity at 0 could bleed over into continuity everywhere else, that's not terribly surprising to me, given my experience with linear data. But continuous, I mean, the connection to bounded, that's kind of like a little bit more like, I don't know, surprising perhaps. But here it is. Of course, 1 implies 2 is immediate, because continuity everywhere implies continuity at all points. If we suppose 2 is true, then by definition there exists a delta greater than 0, such that if we're within delta units of x, that implies that the let's see here. Suppose 2 is true. Suppose it's continuous at 0. Okay, so does continue? Yeah, I mean, so I think we're just basically saying, consider epsilon equal to 1, right? Epsilon greater than 1 is epsilon equal to 1 is positive. So if it's continuous at 0, there exists a delta such that when x minus 0 is less than delta, it implies that t of x minus t of 0, which is 0, is less than 1, right? Okay, so I think this is, again, essentially just the definition of continuity. If x is an x slash, and it satisfies that, then, so delta of x is less than or equal to delta. All right, I mean, I'll buy that. So then t of delta x is less than or equal to 1, combining these two things, right? Which says that t of x is less than or equal to 1 over delta. Therefore, the norm of t is less than 1 over delta. Well, yes, because remember that the norm of t is the supremum of things from the closed unit ball, x being from the closed unit ball, and giving an output of 1 over delta implies that the norm of t can be at most 1 over delta. And of course then 1 over delta serves as a bound for the norm of t, which is to say that t is bounded. All right. And then a proof, I think next we suppose 3 is true, and we give some proof here, which implies that the function is that the mapping is continuous at an arbitrary point, which means that it's continuous. Let's look at the proof. So suppose 3 is true, in other words, t is bounded. Take the difference of t of x and t of x naught. Well, that's, of course, this, which then is the norm of t times the norm of x minus x naught, right? Of course, t is a number because t is bounded, right? So for each epsilon greater than 0, let's just choose delta to be epsilon over norm t. And so if the difference between x and x naught is less than delta equal to epsilon over norm t, then the difference of t of x and t of x naught is less than or equal to what? Well, norm t times that, which is epsilon over t. So these cancel, leave us epsilon. There you have it. We have, for any epsilon greater than 0, there exists a delta such that the distance from t of x to t of x naught is less than epsilon, which is to say that the limit as x goes to x naught of t of x is equal to t of x naught. I hope I said that right. Anyway, I'm trying to say is that t is continuous at x naught. And that is what we need. Since x naught's arbitrary, that proves 1. So, something we should mention, every linear operator on a finite dimensional norm linear space is continuous. But in infinite dimensional case, there exist discontinuous linear operators. And apparently, if we believe theorem 7.5, those must be the unbounded ones. All right. So there are other things that are true about finite dimensional spaces that I'll try to say more when we're in class, but I think I'll leave it at that for now. This is not a, I'm using this script B for Banach space in what remains of this talk, okay? So if B is a normed linear space, which is complete with respect to the norm topology, complete means that Cauchy implies convergent, right? Then B is a Banach space. There are many examples of Banach spaces. Rn, Cn, Lp, even for the infinite case, like L infinity, all Banach spaces. Bounded Bs with the subnorm. I think this is supposed to be S. I think I need to put an X here. I think I need that to be metric otherwise. Right, bounded continuous functions on a metric space. Again, Banach. However, it can be shown, I think they're homework. I probably should pray I haven't assigned them because they're probably really hard. Oh, anyway, continuous functions from 0, 1, it can be shown that this is not complete. Therefore, continuous functions with domain, so real valued. So going from 0, 1 to the reals is not a complete space as it turns out, so this is not a Banach space. So, you know, not everything's Banach. There are non-Banach things. But all right, so the remainder of this section gets kind of, well, dense. And but I think these things are worth mentioning, but I probably won't really prove them here. And I don't really expect you to know the proof of them either. I mean, it's healthy if you do, but if you don't have time and there are other pressures this semester, I understand if you don't. So anyway, here it is. If we have a sequence of continuous linear operators from a normed linear space X to a Banach space B, and the supremum over this sequence is so if the norms of the sequence of operators is if the supremum of those norms is less than infinity, and if the limit as n goes to infinity of Tn of x exists for each x in some dense subset of x, then there exists a continuous linear operator from the whole vector space to the Banach space such that it appears as the limit of the sequence of given operators for each x in the metric space. I said metric space, but I meant norm linear space. My apologies. Moreover, the norm of this constructed continuous linear operator is less than or equal to the lim-inf of the norms of the operators. So this is, and it's a lot to take in, but it's actually a very useful theorem in the sense that it essentially says that if you can find a sequence of continuous operators and you know, suppose we're talking about the domain being real numbers. Well, if you could show that the limit for these operators exists for rational numbers, then that would be enough to show that the there's a limiting function defined for the real numbers, which behaves in a natural way with respect to the given data. I mean, it's a way of bootstrapping your way from rational arguments to all of the reals, among other things. For R2, you could take points with rational coordinates. You know, usually if you look at some sort of rational grid inside your object, it's dense. Anyway, another theorem, Theorem 7.7. If we have a norm linear space and a Banach space, then the space of bounded linear operators from the norm linear space to the Banach space with respect to the operator norm is a Banach space. That's on page 35. So this red remark here is what I was just saying a second ago. You know, if you had this limit exists for rationals, then that it would imply that there is an extension. Well, that there's a function from the whole reals to the Banach space, and it would relate to the given sequence of functions in the natural way. Anyway, there's definitely a homework problem that you'll see in Math 431, which is based on this idea, and in a specific function, not like an arbitrary function, probably. I think the way I've seen it before is something like you get linearity with respect to the rationals, then show that that implies linearity with respect to the reals, or something close to that. I don't remember exactly the homework problem. You'll experience it soon enough. Anyway, and then Theorem 7.8, the principle of uniform boundedness. Here he takes a family of continuous linear operators from a Banach space x slash to a Banach space J, and we suppose that for each x in the norm linear space, that the supremum over this family with respect to that one point x is less than infinity. But I mean that happens for each x, right? Then the supremum over alpha of a of all the operators is less than infinity. There is a difference in what's being said. So I would challenge you to understand that difference. If you understand that difference, that's the first step towards understanding what this theorem is saying. But anyway, this is, of course, a deep theorem. It involves the Baire category theorem. And, of course, my focus is not here, so I'm going to go on. All right. So next up is the contraction principle. I'm going to stop the video here and start again, since I need to get a drink of water.